Thank you for everyone who joined us today. We're going to get moving. So first, a few intros. If you've seen webinars, you've probably seen me. My name's Daniel. I'm the marketing lead in the FX10. I do product marketing for most of our hardware products. 8-9 months ago, Nick and I came here and talked to you about this as a composite printer. So really excited after these months and all this development to come back and talk about it as a metal printer.
Everyone, I'm Nick Morton, and I lead product management here for hardware and materials. And yeah, happy to be back with Daniel and Harrison today to read you all in on this latest update.
And I'm Harrison. I was fortunate enough to be the technical lead for the metal program for FX10, and I'm super excited to be here today to talk about it.
Cool. So first, let's just talk super quick about what we're going to talk through. Pretty simple agenda. So we'll start by giving you a background on metal FFF, which is the actual technology that's on the FX10 that prints metal. Then Harrison and Nick are going to run through a live machine tour. They're going to run through what this machine is like printing metal, some of the differences between it and composite, and most importantly, how you transition between metal and composite. And then last, I'm going to run through some applications, who it's for, and why we think this is a really interesting development with respect to manufacturing floors and potentially you. And then, as I said, we'll end with Q&A. We're going to keep it fun and try to kind of talk to each other and keep a healthy banter with respect to talking about how we developed this, why we developed this, and why we think it's important. So yeah, we'll try to keep it conversational. But yeah, first to you, Nick.
Yeah, so a little bit about how we got here. When you look at what had been available for metal 3D printing before, we started doing metal filament-based printing, it was all million-dollar machines that take up large rooms, have major facilities requirements, big beds of loose powder. So there was PPE that had to be involved. It was difficult to make the process safe. It was a huge investment. We saw, as we were focused on providing solutions for the factory floor and powering manufacturing operations with tooling, jigs, fixtures, and MRO, that there was a need for lower cost systems that were safe, simple, easy to use. So that's what led us to invent metal filament-based printing in the first place. And FX10 is our latest hardware platform with sensorization, enhanced hardware that allows us to whip around the gantry faster while maintaining accuracy and a host of automation features. And we came and launched this to the world as a composite printer at Formnext last November. And now coming here, we're making good on this promise that we had been communicating. Last time Daniel and I were on speaking about the FX10, we talked about how we really made it future-proof, but being pretty tongue-in-cheek without really exposing exactly what was going to come. And now Harrison and the team have made it real so that we can talk to you today about printing metal and composite on the FX10.
Yeah, so when we said hardware and software designed for expansion, modularity, and all these things, we're specifically talking about this.
That's right. So moving from just a composite machine to a machine that can do both composite and metal. And where I think we're really going to see the value come through is being able to expand the applications that you're able to go after on the factory floor. So we've seen a lot of customers over the years go through this journey of starting with industrial composite machines, starting with an X7, realizing the power that can now be harnessed with functional parts that can be used for tooling and hold thousands of kilograms by adding fiber reinforcement, and starting to push that and move into metal over time when they started to see A, the value of additive on the factory floor, and then B, that there were applications they couldn't go after yet because they needed even higher performance with temperature, higher strength, corrosion resistance, wear resistance, applications that simply required metal.
Yeah.
And the metal process that we use here is really a 3-step process. Printing, which starts with the filament that we have here. So that's a metal powder that's bound with a wax binder. So there's no actual loose powder. You handle it with your hands. You don't need any kind of PPE. you load it into the printer just like you normally load a spool of filament. And after printing, which is the same FFF technology that you're used to, where it's a lot like a glue gun on a gantry going layer by layer and depositing filament, you have this green part where it still has the wax binder inside of the part. And we have two additional steps after that. One is the wash step, where we use a solvent bath to wash away 98% of the wax binder that's still in this part. And then the sintering step, where we utilize our furnaces to basically cook that powder metal part into the final metal part.
Yeah, and you notice here there's a scale factor with this. So these parts are the same part, printed and sintered. That's because there's parts of there's parts of that filament that are not metal. So as you sinter the part actually shrinks about 20%. The most common question we get is, do you have to account for that? The answer is no, we scale it up for you. But yeah, so this is the system.
Yep, it's printer, wash, sinter. We've been, selling this package for years now and have built up a lot of experience with it. And, previously this was with our Metal X machine, which is a system that's specially made to print our first generation of metal filaments. And, there was a lot of innovation that went into that Harrison and the team were able to port over and power up in the development of the FX10 that we'll definitely dig into. That wash system right there, that's where the solvent bath is. And then the Sinter 2, that's our high running sintering furnace, where it's basically we're running at high temperature, we're controlling the gas flow that goes in there with inert gas, and that's ultimately what gets you to that final metal part. So 3-step process.
Yeah, and I'll note that the Metal X, while being highly specialized, was developed as an offshoot of composite printers. So we started with this as a composite printer company. The metal kind of came away from that and became its own thing. And the real reason for that had to do with the feedstock itself, right?
Yeah, absolutely. And I mean, when you look at the process, print, wash, sinter, you'll probably recognize this is a page out of the book from metal injection molding. So in that case, the only difference is the actual printing process. And when the team here first developed metal filament, I mean, that was a huge challenge. And one of the things that came out of it was the material itself was quite brittle in the raw form. So you can see it, in the up above the printer in the chamber here on the Metal X. And, Harrison, I mean, why don't you tell us, why is the filament up top? How does that help with the Metal X and what's different now?
Yeah, absolutely. So as a lot of people probably know, composite material is something that is moisture sensitive. So it obviously wouldn't work in the setup we have pictured here, where it's above the heated chamber where you're printing parts. On the Metal X, the system was set up that way because you needed the filament to feed directly into the printhead. Otherwise, it was too likely that the filament would break because of how brittle it is. And so this is kind of what answers the question that a lot of people have of, well, okay, why haven't we done this in the past? Why haven't we had a composite and a metal system? It's because they were basically incompatible with each other. You couldn't put composite filament that's moisture sensitive in the chamber above where you're printing. And you also couldn't put metal filament previously where in a spool bay or in a Pelican case, because it would break in the path as you were trying to print at those speeds.
Yeah, so when you think about this, it started as an evolution of composite printers. What became is something totally on its own, and we spent years figuring out how to print this. At some point, I think we realized that MIM feedstock, which is optimized for pellet form and it's super melting, running into molds, super high volume, is not necessarily the exact same. And we happen to have some pretty great material scientists here. So we kind of pursued our own solution, right?
Yeah, exactly. And that's Daniel's talking about our V2 metal filaments. And you can see here, they are dramatically more durable, even just in filament form, being able to tie it in a knot like this. This exceeded our expectations when we set out for development. And there were a few pain points that we wanted to solve with that kind of first version of the metal filaments. Since it was brittle, you had to be really careful even when you were just handling it out of the printer. And when you saw it in the upper chamber on the Metal X, it also had to be heated. We would heat it up, basically preheat it so that it would be a little bit more durable, and that's what allowed us to print it at all. But now it's much easier to handle, and it's much more durable, so it can be more robust for the printing process. And I know, that was critical for your team, Harrison.
Yeah, no, absolutely. I mean, I think, one of the biggest things that we faced as a challenge is, how do we take this filament that's kind of like a rope? How do we feed it into a head effectively? And how do we make sure it stays intact and that we can print fast parts without breaking this filament? And like you said, or breaking the final part. And this step towards these flexible filaments was a big and a necessary first step in that process.
Yeah, and I think when you think about this, there might be a question. It's like, well, how are these filaments flexible? They're metal, right? So I want you to think about it this way. These filaments are 60% or more by volume metal powder, but they do not, the thing that's binding the metal powder together is the actual binding polymer in the wax. So mechanically, they behave as if as the polymer binder, not as a metal part. And so that means when we're talking about flexibility, we're not talking about as making the metal powder more flexible. We're talking about the binding agents that make it a filament. And so when you're printing a part, what you're really printing when you're melting and extruding is that binding agent. The powder is kind of along for the ride. So what that means is, one, it's really difficult to do because a high percentage of your media that's going out the nozzle is frankly useless with respect to being an FFF printer. But the other side of it is that binding can scale across metal powder. So if you can figure out that binder, adding new metal powders, adding new materials, and bringing them across the line makes a lot of sense. And so if you look at what we did over the last kind of 4 or 5 years, we've really done that, right?
Yeah, exactly. I mean, starting with copper and then bringing it to 17.4, V2, our, by far our most printed metal material, and then rolling that to H13 and D2, and then soon 316L has been awesome. And I think one of the things I'm most proud of on this development journey is that for Metal X customers who are, able to print those flex filaments that we've launched so far, it reduced the jams that we were seeing in the field by 90%. So that was really the number one thing that would, require manual intervention. And now this innovation has really completely paused that, and customers are able to cruise with metal, with the flex filaments.
Yeah.
Yeah, and I think really copper came out a long time ago. 17.4 V2 was probably kind of the watershed moment for us because it was the first time we were replacing an existing filament in the field. So we had tons of data around 17.4, then we released a new thing to the field. And as Nick said, we saw jams decrease by 90+%. That number stayed in the same vein for D2 and H13. But also, interestingly, it freed us up to do a lot more interesting stuff. We were able to speed up the printer, print faster. We were able to print more precise. And so what we kind of did with these flexible filaments and why we said it's such a big step forward is, although they are still very different than printing a plastic, they are closer to plastic than the initial ones were. And so when I think about that, that opened the door for this.
Exactly. Being able to print both, composite and metal on the FX10. And it is, the system otherwise is the same, right? The wash and the sintering furnace. So our customers that already have a Metal X, a wash, and a sinter are now able to add an FX10, and they can use that for composite bandwidth when they need that. And then when they need more metal bandwidth, they're able to do that with the FX10 as well, and really fill up that sinter faster to drive down operating costs on sinter runs by reducing gas cost per part.
Well, kind of like we've talked about, the system, we changed the first step of the system, which is a very critical step, but we still have, a proven to work rest of that system. So it's, we're not reinventing the wheel. We're not going crazy over the top. We're just trying to optimize the use case for that wash and that sinter. And we're trying to make sure, hey, we've got these great products out there. How can we, improve that important first step?
Yeah, I think that's a good way to think about it because, most engineers on the call probably know you try not to change every variable at once. But when you start a fully new process, everything is variables. And so I think when we first launched metal, it took us some time to figure that out. Now we feel pretty confident about the debind and the sinter. We think we have a process that works. And so swapping out the printer and swapping out the way that you're creating the green part is something that shouldn't and will not, as from our experience, be disruptive to the process itself. And partially that's because, frankly, the FX10 as a metal printer is unbelievable.
Yeah, I mean, I don't know if you want to start. I would love to talk about it.
Let it rip, man.
All right. So the FX10 as a metal system is really something that, at least personally, I get very excited about. We're printing up to 2 times faster than the Metal X, and with a larger build volume, your throughput on parts is remarkable. We have automatic material changeover, which means you can print double the amount of spools that you were previously printing within one build, and it reduces the amount of manual intervention you need as you're going back and forth between different prints. Our user interface, we've spent a lot of time trying to optimize how as a user you experience the process of printing. We've tried to make it as seamless as possible so that you're just pressing print and then you've got your part at the end. And I feel like we've really done a good job with this, especially with the number of sensors we put in the system to maintain like a well-functioning system. Even if we expect that something might need maintenance soon, we'll let you know ahead of time. So you don't have to wait for a lead time to get something once it fails. We're trying to predict that ahead of time so that, you have as much uptime as possible. And yeah,
it's definitely
super excited.
A special machine. So faster printing, like historically we've sold that package that Daniel had up with the Metal X wash and sinter for our customers that are running a lot of metal. They've bought what we bundle as a 3-1-1, which would be 3 Metal X printers, a wash system, and a sinter, because at the rate at which we were printing, that was how you would optimize the process so that you were able to fully load the sinter regularly to drive down cost per part. At this point, with the 2x print speed on FX10, the most we'll practically sell is a 2-1-1 bundle at this point, because of the print speeds. And Harrison mentioned larger build volume and automated material changeover. Those really go together because now you can pack the build plate full of parts, do a large batch. You won't need to come manually tend to it to make sure that the next spool is being loaded, and operate, the system a lot more efficiently and bring more value with just one machine.
Yeah. And we spent a long time kind of overclocking the Metal X to go as fast as it humanly could. I think the Metal X as it currently exists is about 4 times plus faster than it was when we first launched it. Even this is twice as fast as that. So that's kind of the levels we're talking about here. Just to give kind of a reference, this part here in my hand, which fits in my palm, it's pretty large, prints in about 7 hours. And I know from experience that if we were kind of in 2018 and we were printing, that'd be a day and a half print. And so that's like the level of the level of throughput and the speed to part fundamentally changes with this type of machine. But it's also been just a bunch of steps in the right direction over time. And so, yeah, with that, I want to kind of stop talking about it on slides and let you guys go actually do some cool stuff. So they're going to transition over and give a little bit of a tour of the machine.
All right. So looking at the system, for those of you familiar with the FX10 as a composite system, it looks very similar. Starting at the top, as far as things that are different, we obviously have a separate metal print head. Unlike the composite print head, where we have one composite nozzle and extruder and then a fiber nozzle and extruder, here we have our metal and our ceramic release extruders and nozzles. So we're able to provide, strong parts that come out of this left nozzle with a ceramic release nozzle that's able to add with the, if you have complex support geometries or anything like that.
Yeah. And for users of both composite and metal, what's the experience like for removing the print head?
Absolutely. So it's super easy to remove the print head. There's just 2 cables to unplug at the top, as well as the feed paths, and then 2 screws. The overall change process of going from metal to composite and vice versa, I think there's 3 screws in total that you have to change. So we really wanted to make it as easy of a transition as possible. And I'll talk a little later when we get to some of the other components about ways that we even removed the need to change between components when going between them. So from the print head, you can see, unlike the Metal X system, the spools are not above the head. They go through a feed path, which is right above the print head, and it runs all the way down through a routing block in the back and then down to the pre-extruders on the bottom. Before we get down there, we do recommend that customers change the purge bins because we want to avoid cross-contamination. A lot of the things that we're changing here, like the feed tubes, the print head, the purge bins, it's all because we don't want any contamination between the metal and the composite printing process. Moving down, you see on the bed, we have the same type of sheet that you would see on the Metal X, but it's obviously bigger for the larger build volume. and you'll see it's the same size and shape as a composite print sheet. So it works in a very similar fashion as those of you who would use an FX10 composite. Same process, still keeping a corner at the front right. It should be super easy. It's kind of a one hand shake. You understand everything all together. Looking at the UI, again, we wanted to keep it as intuitive as possible, as much of a, once you understand one of the systems, whether it be composite or metal, you understand both. So you have the same UI here. The only difference is being it separates once you go into metal printing between showing 4 bays for composite and 2 for metal and 2 for ceramic. And then jumping down to the bays, as I just mentioned, unlike composite printing where you have 4 800cc bays, here we have 2 bays for metal and 2 for ceramic in order to allow for changeover between the two. You can see, actually, I don't know if you can see, but in the bay, there are 2 inlets for the pre-extruder. There is one side for composite and one for metal. So when we start talking in a second and we actually have a dual pre-extruder in our hands, we can talk about what exactly is a dual pre-extruder and how is it important for metal and composite printing. And yeah, you can store your filament in here. You can do automatic material changeover between these 2 bays. And yeah, sorry.
Yeah, I was just gonna say, talk to us a little bit about temperature, how you're utilizing that inside of the chamber on the bed.
Yeah, absolutely. So we have a heated chamber, which for those who print composite can know the importance of that. We also have a heated bed that can go up to 150°C, which is really important for part adhesion and making sure that your parts aren't warping up during your print, as well as making sure you get a really strong first layer. Those of you familiar with additive know how important it is that the first layer of your part be really solid, because if you have something that's either warping up or doesn't print the way you wanted it to, the rest of your part could be compromised. So we made sure to have temperature control for the chamber, temperature control for the bed, and we're constantly monitoring the temperature throughout the entire system, including within the print head, to make sure that components aren't overheating while we're also achieving, our intended temperatures. And, to hit optimal print speeds, we want the right nozzle temperatures. We want to make sure we understand what's going on. And that's a good transition into, as far as the head goes, we packed this thing with sensors. We wanted to have a really good understanding of, how does extrusion work through the sprint head for metal? On the Metal X, we got a really good idea, as we've mentioned before, about how to print metal. We got better over time. We increased our print speeds. And with the FX10 head now, we've just added on to that by adding sensors that allow us to measure the force in the print head through extrusion. We're able to measure how well the extruder is tracking the filament. And it just really has helped us continue to grow on our print speeds and understand what are our actual limitations and can we get past them.
Yeah, and Harrison showed me some exciting data this morning, looking over some of our North Star metrics that we use to track printer reliability, like print completion percentage and how often there are interruptions to the print. And the team has succeeded at driving to reliability beyond what we've been able to do with the Metal X, and it makes sense with that sensor package that you're talking about.
Yeah, exactly. I mean, our priorities were reliability, quality, and then speed. And as far as reliability, the best thing about this printer, in my opinion, is the amount of sensors you have and the amount of information you can simply get from the printer. We're able to not only understand problems more in depth and understand the first principles of the problem to address them and tune for them, but also just simple things about finding what the limitations are the system are. And instead of getting close, but kind of giving ourselves a safety factor to make sure there aren't mistakes, we now know exactly where that line is and we can push right up to it to give you the best part quality and speed while maintaining reliability.
Yeah.
So super exciting.
How has the gantry architecture had an impact on machine performance?
Yeah, so one of the things that we moved to with the FX20 system and then brought to the FX10 is the Core XY gantry system, which allows us to do a lot faster printing with the same precision. So we have a much thicker, basically everything in the system is bulked up from what we did on the Metal X so that we can maintain higher acceleration, higher speeds, but we're not compromising any of that precision that we, is really important to us in getting that quality of parts.
Yeah, it's fun to watch this thing rip.
Yeah.
And on the topic of the sensor package, one of the things that I'm most excited for as a platform for the software team to continue to build and drive new value for years to come is the vision system, which you won't really be able to see from that view, but it's mounted right on the other side of this gantry. And that's used to get, close-up images top down of the parts as they're being printed. We're capturing about 25 microns in each of those pixels, so pretty detailed imagery. And that's going to power, the future, driven by the feedback that we get from you on what's going to be most valuable. But to bring things like what Harrison was referring to with predictive maintenance, or bringing inspection from composite over to metal, and really driving more reliability, utilization, and uptime on the machine.
Absolutely. And just understanding of printing. A lot of times in the past, before we had vision systems like this, it was, you've got to kind of watch it print to understand what the insides of your part look like. And as far as trying to achieve as strong parts as we can and stuff like that, being able to see the layers as they're being deposited is game changing. So yeah.
How about how your team has been able to leverage the machined vacuum groove on the print bed for automating some of the calibration?
That is an excellent question. So some of the other things that are super exciting about this system is, in the past, there's been a lot of calibration procedures that require printed parts. I think that's pretty common in the industry. You want to print a part to understand how your calibration works, whether or not your system is set up properly. We've tried to think beyond that and think, how can we use our system to understand it? So for example, if we want to understand what the nozzle offsets are between our metal extruder and our metal nozzle and our ceramic extruder and nozzle, we're able to do that simply by touching off within this machined groove, because we know exactly what that should be. And so touching off through there, we're able to get extremely precise location of each of the nozzles. And it's all without needing to print a part. It's super fast, less than 20 minutes, and you've got your nozzle offsets, which also helps with, if you're doing a changeover process, it's your first time putting a print head on, you're able to get it up and running just much faster than you would if you needed to print a part.
Yep, exactly. And that helps with the process of changing over, because changing out the hardware that Harrison will walk us through is about a 15-minute manual process. But these automated calibrations that you're talking about allow the user to walk away after the fact and let the printer take it from there for getting prepared to print some metal.
Absolutely. Speaking of, should we look at some of the components in the metal kit?
Set over.
All right.
All right, and we're back. Eric on the camera, props to the Zoom, always super helpful. Yeah, let's talk about the kit a little bit.
All right, so right here, I have a FX10 metal printhead. Get that nice zoom in there. Yeah. So obviously this is kind of the heart and soul of the FX10 metal kit. It's the biggest kind of change that we have because it's what drives metal printing. So we spent a lot of time working on the printhead, and a lot of times there's misconceptions of, oh, the metal kit is just a printhead. It is a small kit. It is a few things, but there are still other critical components that we've worked on. But the printhead is the heart and soul of it. It's what's controlling. It's how we're able to maintain faster extrusion speeds. When we built the entire system, we built it with metal in mind, but we couldn't do metal without this printhead. So that's one of the most important things. There are additional things like material tubes, purge bins, but as far as critical components, one big thing that's definitely needed is this is the routing block. This is important because on the base system, there is a 4-to-1 routing block, because you have 4 spool bays that are going to the printhead, and you could run onyx or your other materials through all 4. Because we need ceramic, it's important to change out the routing block so that you have a metal and a ceramic side. But it's super easy to change out. The way it's designed, it might be too small, but there's a little hole here, and all it is it's just a loosen of a screw, a slide off, and a clamp on. So it's a super easy changeover. It's not a complex process to get the routing block installed, and it's very intuitive to change it as you're changing the feed tubes. And then one of the things that, we talked about how cracking the code for metal and composite together had a lot to do with the filament. But there's still big differences between composite filament and metal filament. Metal filament is much weaker as far as your ability to kind of crush it compared to composite filament. And so trying to run metal filament through a composite extruder would typically result in you either deforming or crushing the filament in a way that is non-recoverable. So with that in mind, we have this pre-extrusion system to feed filament to the printhead. And, we could have just said, all right, there's a composite and a metal pre-extruder. That's part of the swap. but we didn't like that user experience. We said that, you know, that's adding too many steps to the swap. So we developed the dual pre-extruder. And this one might be hard to see. So I'll try to point very precisely.
Harrison, real quick, what's a pre-extruder for the
Totally fair.
uninitiated?
Yeah.
Because there's extruders and pre-extruders.
Sorry, my apologies.
You're good.
So in the printhead, we have our extruder, which is where we control the filament that is directly going into the nozzle and that we're extruding onto the print bed and onto the printed part. A pre-extruder is an extruder that's found down in the spool base that feeds filament to the top where the printhead is and maintains feeding that filament throughout the process of a print. So it's basically part of the process for getting our filament up to the printhead and making sure that our printhead essentially sees filament as if we were feeding it directly in.
Yeah, and
So
and it's a key part of auto material changeover, correct? Right? Because
exactly.
if you have two, now we have the ability to have two load states, right? Like preloaded and then fully loaded.
Exactly. So, you know, when we go through automatic material changeover, you're having one of those pre-extruders pull the remaining filament on a spool as it runs out of the feed path, while another one feeds it in. And so pre-extruders are truly one of the most overlooked but important parts of a printer because they're what supply the material to the printhead. They're what make it as if you were standing there directly feeding filament into the printhead, but you're not there. And so this is, sorry to make you zoom in and out so much. So this is the dual pre-extruder. It might be difficult to see there, but what we have is we have a single motor with a hob on it that has two different feed paths, one for metal and one for composite. And on each of these like idler arms here, we're applying different forces onto each of the feed paths. So there's a much lower force metal side, which is this one. And then there's a much higher force composite side that allows us to apply the different forces we need to get optimal push force on the filament without needing to crush or compromise one or the other. So instead of needing to either lower the forces so that composite filament doesn't have as much control or increase the forces and compromise the material of any metal, we're able to accomplish both. And for those thinking, oh, that's great, but you know, what about moisture? You now suddenly have an open hole that could cause moisture for composites. We've resolved that. We have the ability to plug the added gap. You know, it's super intuitive. And because of this, as you have this in all of your bays with the metal kit, you know, suddenly it really is 3 screws and you are done with the changeover. The hardware swap is, you know, it's 15 minutes as a first-time user, probably decreases after that as you get familiar with it. And, you know, and suddenly, like Nick mentioned, there's some calibration that's completely automated, but it's an incredibly fast change over time.
Yeah, and I think that plug thing is an interesting thing. Those are the type of little annoyances that end up causing issues with the product after you launch it. And one thing that we are really have gotten relentlessly good at is figuring those things out. And a lot of it has to do with this kind of cycle that we have adopted about continually improving the printer.
Yeah.
Yeah, 100%. Well, great engineers are at the heart of it, right? And, you know, watching Harrison's team run with what, you know, used to be when doing development on the Metal X, a really limited set of sensors, to now so much data that we've had the software team go and build an entire platform for processing and parsing the data, has been fun to watch, especially when I start asking the team for more faster, and they're saying, yeah. So that's been that's been special for me. How's the experience been for you?
No, it's been exceptional. I mean, talking about the Metal X, you know, we kind of found ourselves in situations where if there were problems we didn't fully understand, we would build a fixture to try and like add those sensors to the printhead, but it wasn't ever something we could really apply to customers. And so as we built this printhead, we looked at, hey, what are all the things that we've tried to understand, that we've added sensors to this printhead to understand over our time with the Metal X, and we built it all in there. And so, you know, it's become this process where, you know, if a problem comes up, instead of spending a week trying to think of, okay, what are the myriad of possibilities, what could have happened, you know, we, like you mentioned, we have a great software platform that we're able to now use for all of these sensors. We're able to look and, you know, in the morning I spend about 5 minutes, and you know, it's probably only 5 minutes because our failure rate is pretty low. But if we ever do have a failure, you know, we're able to understand what was the cause of that failure and directly attack that, you know, that root cause to try and remove it from customers seeing it.
For sure. And I think those are the key things that make a printer good. It's not always the cool hardware, the interesting materials or the software. It's all three together, and it's people working on it who really understand it and care about it.
Yeah.
So yeah, I think we're a little bit behind schedule, but it's all good. The point of this was to talk about the metal printer, so I'm glad we got a good detailed look. So I'm gonna go super quick on this, and then we're gonna try to still give you guys 15 minutes for questions in terms of all these stuff in the FX10. I see we already have something like 20 questions, so this is we're fighting a losing battle here if we're trying to answer all of them, but we'll do our best here. So first, let's quickly talk about who FX10 is for, why we developed it, and why we think specifically for manufacturers this is a really interesting solution. So let's start with the question. What do you need to do to be productive on a manufacturing floor? A machine, and additive or not, needs to be reliable. It needs to be able to yield strong parts that are also accurate. You need to be able to track the KPIs of those parts you integrate, and you need to be connected to whatever infrastructure. If you're missing these things, it doesn't mean that something is not valuable or not interesting or not useful to have, but it means that your ability to actually integrate it and see value out of it is greatly diminished. We talk about this idea that a 3D printer often kind of sits in the corner of the factory and just does stuff. And that's a cool thing to think about, and a cool kind of mode for 3D printing to be in. But the reality of the situation is, if that's what you're doing, it means that it's not actually maximizing the value that's being put in. So you really need all of those things together. And if you can't trust the printer to yield strong and accurate parts, well, what's the point? It's just a toy. So when we think about metal and composite on a fundamental level, they complement each other. They really excel at different things. And that's not to say that metal is just better than composite at everything, or composite's better than metal at everything. They have different strengths. So when we think about composites can print relatively large parts. We kind of beating around the bush here with respect to throughput, but you really don't. Metal X or Metal FF process-wise has a kind of maximum part size that has more to do with the physics and the sintering process than it does with the printer. Composites is better for large parts. If you need a part that has design compliance, so you need to beat it up and it needs to be able to flex and not break, composite's better. Non-marring, composite is better. And then generally composites are cheaper and faster than metal, because metal is still a three-step process. And the last thing I'll say is, as printed tolerances on composite are almost always going to be tighter, because again, your process on metal is 3 steps. And so even if you print a perfect part, sintering is a process where shrinkage happens, and we try to be realistic about what the tolerancing is, and we generally say near net shape. On the other side, metal excels in places where simply it's metal, right? If you need something that's ultra high strength, right? Carbon fiber is strong. It is not as strong as steel. If you need something that's really hard, we print D2 tool steel that gets up to 55 HRC. I don't know the exact value, but it's well up there when you heat treat it. Likewise, abrasion resistance. So if you're thinking about production tooling and you're really working with something and doing thousands or tens of thousands of cycles, well, it might work perfectly the first time, the 1,000th time, but maybe the 50,000th time it's worn away enough that composite is going to do that. And the last thing is machinability. And this is a little counterintuitive, because we said the tighter tolerances off the printer are better for a composite machine. But if you need the tightest possible tolerances, the best way to do that is to print a metal part and then post machine the parts that you need to be tight tolerance. Because composites and our plastics, and plastics are not fundamentally easy to machine. We print with usually nylon-based materials, and that is not something that you can generally hit tight tolerances with off a machine.
Mm-hmm. Those are some great points, and it, like, the way that it often plays out when we're working with customers and talking through applications is actually steering towards composites for a lot of applications that people thought were previously only possible with metal, because of the strength that you can get out of those parts, and the ease of use is just so much more turnkey.
Yeah, and I think the way we think about it is, when we talk to customers about this, we talk to prospects about this. Composites can solve many problems, probably many more than you think they can solve, but there are applications in just about every vertical and every space that just fundamentally need metal.
And that's the beautiful thing about FX10 is now you don't need to decide. It's no longer a question of, oh, do I solve 80% of these or 20%? Now you can solve 100% of those problems.
Exactly. And so Harrison hinted at what we're getting at here, which is, let's talk a little bit, when we think about mapping these to applications. And again, this is like a very reductive view of what the applications are. I just want to talk about this quickly to give you kind of a big picture as to why it's impactful to have both. On the composite side, here's 3 kind of applications that make a ton of sense and why they do. So end of arm tooling has always been the killer application for composite parts. They are high complexity. Being able to customize a part actually can cause you to have performance improvements on a line. Often we think about 3D printing as replacing cheaper, faster. This is replacing higher performance on the end.
Yeah. Lightweighting, combining multiple parts to one.
Exactly.
Yeah.
So you talk about performance here. Another one, and this is a huge group, is conformal work holding. So this could be everything from soft jaws to welding fixtures to assembly fixtures to CMM inspection check gauges, all of these type of things where having something that's able to grip conformally increases your ability to perform. And it might be something you need to machine, and machining conformal stuff is a real pain. And then the last thing is really factory aids. Factory aids are the type of tool that you see everywhere, that is hard to define as a single thing, but is critically important to a factory running, but extremely expensive to make. So here's an example of at a food and beverage plant. You can see all these parts in this right picture. Those cup parts are printed. That's not really a named part. They probably have some name for it there, but it's brackets, it's sensor mounts, it's guides, it's shrouds, it's covers. It's these type of things that are important to making a factory run, but maybe are not the things you see on the front side. And the fast lead times on composite here make changeover faster, and they mitigate line down situations. So if you have something that breaks and you can print a replacement in composite really quickly, that's a thing where composite is advantageous. On the metal side, the applications get a little bit narrower, and that's probably because the part cost is a little more expensive, the constraints are a little tighter, but when you hit the right application, it's super impactful. So these three are really super specialized tooling. So this thing is a fish descaler on the left. And some tools, you just cannot optimize, and you need additive to be able to optimize. They might be something with internal channels. There may be something with super complex geometry that wouldn't work any other way. And they might be something you can only 3D print. So for these type of tools, it can be super valuable to print them. And even though the tool cost is higher, the ROI is much higher. And metal's durability and robustness in these cases exceed what you can hit with composites and enable you to access applications that otherwise you wouldn't think about. Likewise, the other two are kind of smaller application spaces, but very interesting. Complex prototyping, if you have the right parts and you really need them to be metal. We talk about composites as a functional prototyping thing. Well, if the function you need is abrasion resistance, hardness, temperature resistance, the part is metal and you need to prototype it in metal. Metal 3D printing is a useful thing there. And the last is super high mix end use parts. These can be like super high fidelity parts. This example here is Goering, who makes end mills. And so they're able to take on new customers because the end mills that they are making are too low volume and too custom to justify the tooling required. And by printing the tool bodies and then brazing carbide tips, they're enabling themselves to make tens of a tool instead of hundreds or thousands. And that enables them to open up new business lines, make more money. And so these are kind of the three faces for metal. But what I really want to talk about with a little bit more time, so we can give our time for questions before we finish up, is the kind of holy grail of both of them, which is hybrid parts. So we talk about metal and composite separately, but in reality, the combination of them is far greater than the sum of its parts. So I will talk super quick about this, but tools, there's basically a ton of different application spaces where there are aspects of tools and fixtures especially that make you need the best parts of both metal and composites, but are inaccessible if you don't. And so examples of that are tools with hardened wear pads, where the tool does not need to be fully metal. Metal is expensive, metal is inaccessible, but there are parts that contact the workpiece that do, because otherwise the composite part's going to get shredded. It's not really going to work effectively in application. Tools where you can leverage the precision machinability of metal to print a custom metal insert, or something where the face of the part is highly precise, but you still have a body of the part that's composite. And then the last one I'll talk about is you can utilize the non-marring aspects of composite and print metal tool arms so that it's a highly robust tool with swappable wear pads. Nick, I know you see a lot of factory lines. How do you see these hybrid parts really optimizing people's workflows?
Yeah, so one great example that comes to mind is from one of the largest automotive OEMs in the world, and they were optimizing their line because they wanted to make it more ergonomic and reduce cycle time when they were installing some of the bolts on the axle assembly onto the final vehicle. And this is a customer that's actually a power user with composite, and they started out doing this with onyx and carbon fiber, but found that their operators are doing this function 1,000 times a day, and that's one where they were having the problem with wear resistance, and were able to replace it with 17.4 V2. Another one that comes to mind is for one of the largest elevator OEMs in the world has started. MRO is tough, especially for products that have a long lifetime like those. And they have these specialized parts. They need them at really low quantities. And they told me they straight up get no quoted all the time. And so they found, wow, this was a way to take the supply chain and bring it into their own hands.
For sure. Yeah, I think this is like when you think about using these together and leveraging, I hate to use the word synergy, but the synergies between them, it is a legitimate place where it makes sense. And the last thing that we'll say before we open up to questions is this. We talk about FX10 as kind of the most versatile tool for your factory floor. When it was just a composite printer, I think that was a little bit of a stretch, not in that it wasn't highly versatile, but there were things that it couldn't do. But now when you think about this machine, and 3D printers broadly as Swiss Army knives. Well, this is the only machine out there that's printing both composites and metals. That means that you can do all these applications we talked about. You can cover each year's own weaknesses in application. And probably last and most importantly, there's optionality here. You can buy this as a composite printer, or you can buy this as a composite and metal printer.
Yeah, no, and I'm super excited to see, because I expect that there will be a lot of customers who get the composite system and they get super excited about it. And like you said, they find, actually, wait, maybe I do need metal. And I'm confident that as customers get this, they're only going to see more and more value coming out of it.
100%.
Yeah. So I think now we have one kind of reference slide. If you want a screenshot, this is our industrial offerings right now. You have X7, you have FX10, you have FX20. X7 is a composite printer. It's been around for a long time. It's highly reliable. It's a great machine. FX10 is the one that does metal and composites. And then if you need high temperature composites for aerospace applications or super crazy composite tooling, this is somewhere where FX20 comes in. So yeah, with that, I think we want to thank you for spending the time with us today. And we'll open it up for as many questions as we can. It might be a little shorter because we talked for too long. But yeah, so please use like the Q&A part, and I will try to rip through as many as we can in the next 10, 12 minutes. But yeah, thank you so much for your time, everyone. Really, really appreciate it. Let's see. And so just generally, if there's a question of does it print in X material, will it print in X material? The materials we talked about on the flex material side are the ones we're printing with. We're planning on printing it. We're starting with 17.4 and then kind of bringing the rest to FX10 over the coming months. But so I'm just going to say just broadly, no, we're not doing it. But there's always maybe. Okay.
Yeah, I expect we'll have, for the stuff that's already in our material library, I expect we'll have it all rolled out within 2025. Yeah.
So there's a couple of questions around shrinkage. Does shrinkage make it difficult for repeatability? Does wall thickness determine shrinkage per aspect? So both of those, it is more repeatable than it is accurate, as pretty much any 3D printer is. And then in terms of wall thickness, it maybe has an effect on how it shrinks. You can print solid parts on our solution, but it really changes how the part's printed, how long it takes to debind, all that stuff. But it's possible. It doesn't necessarily change the shrinkage.
Yeah, and I would just add to that to say, like you said, the repeatability is kind of more there than the accuracy is pretty common. But with the options we provide, we've tested and tuned these so that we really do have a good understanding of what the shrinkage will be.
That's right. The bottom line is we've got the team here that makes the hardware, formulates the filament, manufactures the filament, writes the software, does the print tuning. And the whole purpose of that is because we're focused on the factory floor and making it a just press print experience. So you load the end part that you want, and that's what we compensate and produce.
Yeah, a couple questions about facility requirements. So the printer, I mean, we have it here in our video studio. So the printer you just plug in, it works. The debind and sinter do have facility requirements. So the sinter requires 3-phase power. Both of them require ventilation. The one thing I'll say is if you're in a well-ventilated room already, then you can use a filtration system from a company called BOFA. It costs a few grand, and that's a little bit easier if you can't drop ventilation. Okay. Is it possible to apply any heat treatment to the parts to increase mechanical properties?
Yes. I don't know how you're testing me on which ones can and cannot, but yes, we are able to heat treat, I believe, 17.4, H13, and D2. And I'd have to double check on copper and 360 now.
Yeah, and the change to the hardness values is on the data sheet for those materials. So
exactly.
You can check that out.
Generally, if you can heat treat a metal that exists in normal and rot form, you can heat treat the metal here.
I mean, we talked a little bit earlier about MIM, and fundamentally, the metal and the metal powder that we're using is the exact same. The process for getting your end product is different, but we're talking about the same metal.
For sure. A couple questions here. One is, can you print metal and composites in the same print? No, the systems are different. So a cool idea that we've heard quite a few times, not feasible, unfortunately. What's the max metal part size? So here's what I say with part size. The ideal part size for metal printing is like the size of your thumbnail to the size of 2 fists next to each other in any orientation. You can go larger than that. You can see some parts on the table here are pretty big. But the larger the part gets, the more expensive it gets, the longer the lead time it is, and you start to get into questions of how is the part viable from a sintering perspective, and is it economically reasonable to print?
Well, I think just adding to that, geometry is a huge consideration when it comes to that. Like you said, the sinterability, you want to make sure your part won't collapse. So a lot of it does have to do with the geometry. I think at Markforged, we're very open to conversations if there are parts that you are trying to achieve, and we want to see if we can make it happen. But as far as size, it's a very difficult question because it depends on what geometry you're trying to print.
Yeah. Okay. And next, I see a bunch of questions about price. Ballpark for composites, it's like 120 all in. Metals, like about double that. And if you kind of did one and then the other, it's about the same. But I will say it depends on region. It depends on where you are and what install you get and what support plan. So if you want to quote, reach out. We'll reach out to you. And if just tell them you want to quote, and we can kind of get in touch about that. That is the ballpark though. And then I've seen a bunch of questions around comparing to powder bed. So I guess you guys want to take a quick hack at how do we compare metal FF to powder bed?
Yeah, 100%. I mean, they are really suited for different application spaces. Powder bed fusion, I would say, is good for larger, highly complex parts, big, aerospace heat exchangers and nozzles with big contours. On the same token, it's a really complicated system. You're looking at probably $1 million investment, some major facilities overhauls, and I think that's good if you're one of those aerospace customers or a defense customer that really needs those application requirements. Or if you just need a few of those parts, then it makes sense to look at like outsourcing to a shop that specializes in running that system. It takes a lot of training, and for metal FFF, it's better suited for high mix, low volume, part size 2 fists or less. And the trade-off is that you're able to get it with a much less expensive system that's simpler and easy to use. So it's practical to actually bring it in-house.
Cool. Okay, let me see if there's any other questions that we're having. What's the most precise part we've ever made in metal, and what tolerances? Kind of like we said, if you're printing to tight tolerances or you need tight tolerances, the way I think about this is it is near net shape. So the closest technology in terms of pursuing tight tolerances would be casting, right? So if you want to cast it, like you need a part with complex geometries that you cast, but you want it to have super precise dimensional accuracy from maybe face to face or a hole, you would then pursue some post machining to do that. So if it's a hole, you might ream it out. If it's 2 faces, you might just see it like, surface mill it. There's a bunch of ways to do this. If it was a profile, you might turn it. So that's how I think about it. Within that, it's achievable to reach whatever tolerance you can achieve machining it. The one caveat we'll say is when you do that, you have to be careful. You have to make sure you thicken the walls and all that. And as kind of a related note, someone asked, what's the max infill percentage? So you want to talk a little bit about like solid versus infill?
Yeah, so we do offer both a tri-fill and a solid fill options. Like Daniel mentioned, if you go with the tri-fill option because you want a bit lighter of a part, you can control the number of kind of the wall thickness to make sure that if you are going to post-process and post-machine the part, you have the ability to do that. But yes, we do offer both a tri-fill and a solid fill densities, which as far as how solid it is, I don't know, you're not going to get it's not going to be apples to apples with a subtractive part because you'll always have a bit of loss of Z strength because of, layer lines, as is always the case with additive. But like we've mentioned before, we spend a lot of time. Part of the reason why we bring this whole process in-house is so that we can spend time understanding the filament and getting as close to perfection or as what we would consider perfection as we can. And so with the solid fill, we hope that people would say, all right, yeah, I want a solid part.
Yeah.
Let me print it.
Yeah. And a couple of great points that reminds me of, especially going back to that powder bed fusion question, is because we're printing with this filament-based process, we are able to print parts with infill, which means a much lighter part, a lower cost part. You're not having to use as much material. And when you're doing that, it's going to be able to sinter faster. But for sure, if you really need a solid part, you can print it solid.
Yeah. A few more questions. We're running right at the edge of time. I want to stop by 11 to let y'all leave. Someone asked, is Markforged dealing with a composite and metal machine currently? I would say on the industrial side, 100%. There are definitely OEMs who have advertised the ability to print kind of metal filament. And while I think that is possible, the devil is really in the details with respect to metal FF processes. You need to control every aspect of the process, the print, debind, and sinter, to really achieve any sort of reliability, accuracy, consistency, all that stuff. So yes, there are maybe some other plate, like you'll see somewhere that has advertises a metal filament and prints it and says you can use it, but that doesn't necessarily mean that your ability to yield metal parts at a reasonable time frame, at a reasonable fidelity is there. And then the last question that we got is all around shrinkage. So let's finish with shrinkage. Essentially, people are asking, is it repeatable, is it reliable, and all that. So let's talk super quick about what it is. So I kind of mentioned this, but we scale the part up 20%. If you take 1.2 and cube it, or you take 0.8 and cube it, you realize that what that means is that we have somewhere in that 60% range of metal powder by volume in the part itself. So the rest of it is because hopefully consistently distributed polymer and binding material. So now I'm going to give you a bunch of hypotheticals. If the metal powder is perfectly distributed, and if you were in a world where there was no forces on a part as it was shrinking, it was floating in space, it would be a relatively perfect shrinkage. Obviously, those aren't true. So what are the variables we can control? We can control powder consistency, so we work really hard on being good at that. The next thing that we can control is the effects of the forces on the part. So what are the two forces? They're gravity and friction. So what do we do to control those?
Yeah. So when we're printing the part, like we said, as we mentioned before, there are a lot of sensors. And so as far as controlling for gravity and friction, being able to sense and understand what forces we're seeing as we extrude is incredibly important, and can actually also help with understanding, kind of like you mentioned, the powder distribution.
Yeah, for sure. And if you think about it this way, friction is the interaction between the part and the base of the sintering and the sintering process. We use basically a raft and ceramic interface supports. And so that enables us to control that. And from a gravity perspective, you can never beat gravity. We all know that. But what you can do is you can understand it. And so someone also asked about education and all that kind of stuff. We have a design guide for metal that applies across platforms. And we also have pretty good education on what it means to print with Markforged, composite metal, all these things. The last thing I'll say to close off is that the best thing about this printer, beyond the fact that the capabilities exist, is that they are both FFF printers at their core. So that means that the rules of the road, while they are different in many ways, come from the same first principles. So the first principles about printing a great part exist very similarly in composites and metal. So if you know how to print composites or plastics well, you can scale your knowledge to metal. And it means that if you want to learn on plastics and then go to long strength composites and go to metals, you can do it on a machine like this. And so what we care about more than anything is bringing this type of additive manufacturing to manufacturing floors in a meaningful way. And that's how you do it. You build strong machines with quality materials and good software, and you make sure that people can educate themselves in a meaningful way. So yeah, I think there's some other questions. Unfortunately, we're already at time. We'll take all the questions down and we'll reach out and we'll try to answer them best we can. But from me and from everyone else, I want to thank you for your time. You guys have always been great. And yeah, hopefully you learn more about these machines and kind of get moving on buying one. That's the dream.
Super excited to see how people like the machine once it's in the field.
Yeah. So thanks for your time, everyone.
Thank you.